Okay. Hello. So we're a little late, so I'll try to. We're a little late, so I'll try to speed up a little and limit my part to the absolute minimum. I'm Harald BIER. I'm Secretary General of the European Biochar Industry Consortium, which is the European Association for Biochar. I've been here at the first event when they had the first Biochar pavilion, and Paul just told me back then there was 8 companies. Now you see how much it developed. So back then we were discussing biochar carbon removals in this CDR environment a little, but it was just there seems to be something that's speeding up our markets. But it was really at its infancy. And that's just 4 years ago. And now we see ourselves at a totally different point. CDR has really gained importance, and BCR is, well, it's just the one that's realizing the most sales, actually. Like the realized carbon removals are over 90% based on biochar carbon removal. So coming from a point where, yeah, we knew that there was something that could remove carbon from the atmosphere and contribute to, well, basically be a climate service, which could be monetized somehow, from a rather juvenile perspective to something now which has grown, which has professionalized and developed tremendously. Exponential growth, I've learned that it changes your reality every couple of months, and this has happened now since we first met a few times. So now I'm really happy to be here with some of the great figures and people representing some of the main associations and organizations of this field. So we have Carbon Gap here, Sylvain DELERCE. I really like Carbon Gap. We have very good relations because they just have this tech-agnostic approach. What works, what are good CDRs, what is high quality carbon removal, and they really do a great job in promoting that and setting the boundaries somehow. He will start his presentation. After that, Ueli STEINER. EBC was one of the first who had, like EBC Sync, one of the first organizations that had helped us monetizing the biochar carbon removals and setting a framework where you have trustworthy carbon removals. And he will present how far they have come. And then SANEI, we've been in contact since almost 2 years, and he's been working intensively in showing the permanence of carbon removal through biochar, like biochar's permanence in the environment, through 2 publications, recent ones, of greatest importance, I would say, for our sector. So I will not talk any further. I would leave the floor to Sylvain. Thanks for being here.
Thanks, Harald. Good morning, everyone. It's a pleasure to be here. Thanks very much, Harald, for the introduction. And I understand that we are a little bit late, so I'll try to keep it to the point. So thank you very much for being here. So in this session, we are exploring how biochar has matured, as Harald described in his introduction. And I think overall, the CDR industry since 2019, we may say, has really taken off. Everything is growing. We have more people, more projects, more transactions, all of this, which is excellent news. But of course, it brings new challenges as well, as things are growing and reaching another level of maturity. So in this first presentation, what I would like to do with you is to just step back a little bit from just biochar and look at where CDR is at right now, because of course biochar is part of the crew and is leading the pack, you could say, as Harald was suggesting. Yeah, have a look at this to look together at what comes next in this maturing process. Okay, this is working. That's excellent. Very quickly, Carbon Gap is a European NGO. We focus on carbon removal, all kinds of carbon removal, and our mission is to help accelerate the deployment of carbon removal capacities in Europe with ambition, but also with rigor, which means that we are also very interested in looking at how things are done. All right, so let's kick off. Some context to start with. With COP28, we've had the global stocktake, and it was just another reminder of where we are at now with the fight against climate change. Global emissions keep rising. The remaining carbon budget is shrinking, and therefore our dependence on carbon removal to stabilize the climate is rising. And all of these are bad news, which is why they are in red. As you can see, the global stocktake, which was released and approved during COP28, identify a gap between the level of emission we are still having and the one we should have of about 20 to 23 gigatons per year by 2030. And the global emissions have not yet peaked. So you know this notion of carbon budget is a very important one. You know, discussing carbon neutrality by 2050 does not really tell much about what has to be done, actually. The carbon budget is a much more powerful concept. So scientists have been quantifying this remaining carbon budget over time, and of course it is evolving. So starting in 2020, we had about 500 gigatons remaining that we somehow can spend. And it was actualized last year, and it's now only 250 gigatons, approximately, gigatons left to be emitted if we want to stay in line with the 1.5 climate objective. So linked to this concept is, of course, the level of carbon removals we will need to achieve the stabilization of climate. And again, this has been quantified in the last assessment of the IPCC, released in 2022. And it is estimated to be between 5 and 10 gigatons CO2 per year by 2050, the removal capacity we need to develop if we want to meet our goals. That's massive, particularly compared to what we are doing right now. And this is bottom left on this slide, where the report State of CDR released in 2022 suggested that we are currently removing about 2 gigatons per year of CO2, but more than 99% of this is done by natural systems, and so forest and natural land-based methods, and only 2.3 megatons CO2 per year are removed with permanent removals. So we see the scale of the challenge and how fast these activities have to grow. Then another reminder, not to, to be pessimistic, but that's the reality. Climate change is accelerating. Temperatures are rising, and you see how 2023 was kind of an outlier in this trend, particularly over the summer. And that means that has also impacts on the systems, and particularly the natural systems we intend to use as carbon sinks. In this case, you have a map of the French forests, with some of them showing clear signals of a decreasing capacity to suck carbon out of the air, and of the air, and some of them have already turned to be net sources. And that's a major issue, and believe me that the government is right now struggling with this, because it is actually threatening our goal of net neutrality by 2050, because this is the main things the government has been betting on, you could say, so far. So that's a major problem. On the other side, CDR, as we said, has been growing and is increasingly recognized as the third pillar of climate action. And it's materializing as well. Numbers are growing in terms of sales, number of tons, deliveries as well. And on the bottom part of the slide, you have a little bit of a photo show of 2023. This is the new plant of Net Zero in Brazil, which I think is one of the world's largest right now in terms of biochar production. This is the inauguration of the direct air capture plant of Heirloom in the US. Heirloom is using a very different concept to capture CO2 from the air than what we are used to, with Climeworks, for example. This is Planetary. This company is piloting ocean alkalinization in Cornwall in the UK in 2023. This is a container, and I mean the demonstrator that Repair, another DAC company, launched in 2023, moving their technology, which is based on electrochemical DAC, to a TRL closer to 6 than lower, which are also good news. And this is a picture from Litos in the US, where basalt is being spread over crop fields to do enhanced rock weathering. So yes, the industry is moving forward, and that's excellent. And as I said in the introduction, that comes with new challenges. So it means that if we want all this capacity that we are deploying to achieve a good climate outcome and to be trusted as well, we need to put in place a robust governance of these activities. So there's this question floating around, which is, on the long run, is CDR a limited resource that we should manage as a public good, or is it an abundant resource that we can deal with much more like a commodity? And on the long run, I would say the debate is valid. But in the short term, it is clear that CDR is a limited resource. We said that in the beginning. We have a very little capacities right now to remove CO2 permanently. And that means that up until we have massive amounts of CDR or we have stabilized the climate, we need to put very robust governance around this if we want to make good use of these limited capacities. So it means that the use of CDR should be mostly targeted at compensating for residual emissions. The small icons refer to something that maybe you've experienced. This is a huge rabbit hole and a very complex debate. Residual emissions, how you define them, based on what criteria. So that's an open question that is not yet resolved, but we need to resolve it very soon because it is somehow cross-cutting all the climate policies. So we need to know what these residual emissions can be. And they can, CDR can also be used to address legacy emissions, to restore, in a way, carbon budget for us, for other countries, for other actors that will have a harder time decarbonizing. So for that, there is a principle that is very important that we call the like-for-like principle. And the idea is that if you're compensating for a specific type of emission, the type of CDR that you're using for that needs to match the characteristic. Particularly if you're compensating for fossil emissions, you need to use high permanence CDR. So that in turn opens all the debate about permanence that has been very active on biochar and evolving quite fast. But I guess the point of this slide is to say that yes, the inherent characteristics and permanence of CDR methods is important, but that's not everything. That's not enough. We need, as I said in the beginning, to regulate somehow the use of the CDR credits if we want them to deliver a proper climate benefit. So yes, there needs to be a like-for-like principle with the permanence, but in between, we also need a continuum of MRV, so that's monitoring, reporting and verification protocols to prove this quality, and then also liability mechanism to guarantee this quality over time and long time. And the truth is that some CDR methods are struggling not with the permanence side and I would say the scientifically demonstrated permanence of their method, but more the bricks in between, how you demonstrate it. One example can be ocean alkalinity or enhanced rock weathering, where we know in theory and on paper this is highly permanent, but how you demonstrate and quantify this is a huge challenge. The liability issue is another one that I guess all the spectrum of methods under the carbon farming is struggling with. Biochar that could also be a challenge for biochar in a way. So just to highlight that we need this full continuum if we want to have a proper governance of this use of CDR. And the use needs ideally to be registered and on registries that are accessible and open access so that the society can scrutinize a little bit what's being done and how the units are transacted and used. So some of these topics are being addressed under what is called the Carbon Removal Certification Framework. That's a policy proposal that is currently under negotiation at the EU level, and that should be voted very soon. It's right now in trilogues. And we've been very active on this file. CRCF is a very good step forward, but still it has some limitations. One is on tech openness, so that's in the definitions. We will see what comes out of the last steps, but there were some issues about restricting a little bit the methods that could somehow be covered by the CRCF. And it falls short also on the uses, this question we were just looking at on this slide. I'll move forward. Again, as this sector is growing, governance is important, but I guess we'll discuss this all across the day, but demand is also very important. We need to design a large-scale sustained demand if we want the CDR project and companies to be able to keep growing and investing. If the landscape and the visibility is not good, investment will probably stop or slow, and that could compromise the pace of development that we need. So right now, CDR is mostly operated under the voluntary carbon market, which has very little rules. And this market is in transition right now. There is a shift toward quality credits, mostly linked to different news that we've had in 2023 and problems of rigor and delivery on the voluntary carbon market. And so this market is here. It is pulling CDR right now, but there are some uncertainties on where it's going and how it will evolve and what will be the motivation for buyers in the future to keep buying significant amounts of CDR under this kind of markets. Another topic here is the topic of claims that companies can make when they buy CDR credits. And this, again, is evolving very fast with a lot of regulations coming in, particularly at the EU level, that will potentially change a little bit the rules of the game. So it means we need to gear up demand and design other kinds of mechanisms to have more demand for CDR. One, the next step we could say is public procurement. Public procurement is when government purchase directly CDR with conditions, of course, and it has different advantages. One is that it validates the recognition of CDR as a climate solution. It acts as a standard setter, so it defines what goods look like when you purchase CDR. And it can also help to fund some CDR methods that are far from being competitive right now on the market. You have examples here. The US is moving very fast on this. They already have an operating program of about $35 million, and another bill has been filed at the beginning of this year to scale this up. Then there's the question of compliance markets and mechanisms that will bring a whole lot more of demand. As soon as things become regulatory, a lot more actors will have to buy CDR, and that will bring a lot more demand online. So here again, this can take very diverse forms. It doesn't have just to be a market. This can be requirements embedded in value chains, for example, as they did in the state of New York with concrete. Okay, I'll move fast. And then, yeah, if you look long term, then there is another question that needs to be addressed, which is how we organize long-term demand more in a way of a waste management problem and an effort sharing schemes. Okay, last slide, I guess. Something that we also need to keep in mind is that, yes, we need to push our methods forward, demonstrate the value, develop all the continuum of MRV and all these techniques, but at some point there needs to be some strategic planning. The resources are finite, and we experienced that with in preparing this study that you see here, and that will be released at the beginning of March by Carbon Gap on France, where we try to estimate the potential of the country to deploy CDR, all kind of CDR, and very quickly you bump into issues of limited resources with competing demands. Biomass is an obvious example, and so if we want to make the most of these resources, there need to be probably some regulation. It cannot just be free market, otherwise we will run into obvious problems. So just to highlight the importance of this strategic planning and take into account these trade-offs and competition for resources. I'll wrap up here. The takeaways were just, playing a little bit on the title of the session. I just added this question mark. Yes, game-changing evidences, but again, you have this all broader context that you need to keep in mind. CDR methods prove their value, as I said, but they need to do the whole chain of quality, MRV, liability, uses, and registries. Strong case for cooperation. That means the problem of demand. We can compete on existing markets, but much more than this, we need to expand markets and demand. So we need to cooperate to make the case and because these compliance mechanisms come from central powers and governments, so this needs to be advocated for. And finally, this need of supervision and some coordinated growth so that we don't just run into competitions and problems of fighting for the same limited resources for different methods. Thank you very much. I'll stop here.
Thank you, Sylvain, for this wonderful mise en context. I could just go on with the discussion because I have noted down a couple of points, but I'm discussing with your colleagues already. Thanks a lot. So I will just pass on to Ueli STEINER of Carbon Standards International, who will tell us how they do that in practice.
Yeah, hello everyone. Thanks, Harald, for the invitation to this presentation. Carbon standards, what we are doing, we develop biochar standards and standards for carbon dioxide removal, and Harald asked me to speak about the next generation of standards. Let me start with biochar. The next generation of biochar standards, in our point of view, allow to produce a high-quality product, high-quality biochar, a certified biochar that can be used in different applications, can be applied everywhere, can be a soil application, can be used in agriculture environment, can be used in the industry, should be used everywhere where biochar is generating an additional value. I think this is the point. Let's produce a product in a good quality and let's add the product somewhere where this biochar carbon is generating an additional value. Our European biochar standard is more for the European market, and the World Biochar Certificate Standards is outside of EU and EFTA countries applied at the moment with different quality classes. What we need on the production level is the possibility to manage this. I think it's always a little bit based on our experience in the last 15 years. It's important to give an instrument to the producers that it's easy for them to manage the production, manage the feedstock, production units, systems, and at the end, even the stock of the biochar that they produce, and it will be a part of the next generation of biochar standards in our point of view. Okay, let me jump in carbon dioxide removal standards, because this is the important topic today. The next generation of such standards contains the possibility and open the possibility to certify long-term carbon removals. We will hear today what that means, and also temporary carbon removals. There are these two, as we have heard just before, these two options out there in the market, and the next generation of standards has to cover this. Of course, there has to be innovations in, as example, in the new biochar standard from us that we will publish in the next weeks. There will be a C-Sync efficiency label of the product. It's a mix of carbon and energy use of the feedstock and what ends up in the biochar. We need innovations in, that's clear, but at the end, the big difference is if it's a long-term carbon dioxide removal or more, a temporary one. Okay, it's winter time, snow sport is going on. We have a global C-Sync sports team based on snowboards in the World Cup, and our athletes, they have snowboards with biochar in. Global C-Sync, you see the logo over there. Yeah, it's the proof, it's biochar in, it's not only carbon neutral. We created additional value in this snowboard based on the carbon, the nanocarbon, put it in, and yeah, we have quite good results, and more athletes are interested in having such a board. What's this? What kind of carbon dioxide removal? Harald, how long do you have your... You are a snowboarder. How many years?
I am. I'm probably the snowboarder who keeps his boards longer than anyone else. So my current one should be about almost 15 years.
Good.
So
Then
I'm kind of the exception, I guess.
yeah, we will give you one. Then you have it 15 years. It's a 15 years carbon dioxide removal element that we can have on our planet. And there are many others out there. Can be windmill propellers, can be in the car industry. All of this are temporary carbon dioxide removal and has to be part of such a new system of standards. Of course, in our standard family, we have other standards really important on the planet, not only biochar for the industry, also artisan for the developing countries, global south, production of biochar, and also here we have the temporary part and the long-term part. 3, as we have heard just before, replantations. Again, it's an important topic. Also for that, we have a standard in our family. And also here, a tree plantation. It's a temporary one. It's a temporary carbon sink. We can, of course, measure every year everything what is in, and it's clear. Registration, if you come back to the biochar and we have a soil application in this case, then it's fully clear. It's a long-term carbon sink. We will hear more in the next presentation about persistence of biochar, how it has to be done. But also in the biochar sea sink, there is a kind of temporary part, and the discussion about is ongoing. How much is it? But it can be registered properly and also sold as a carbon dioxide removal in the market. If we jump into the next slide on the registration, if we have a look, as example, on a tree plantations, a replantation of a new forest or something, then what you see here is also a temporary carbon sink methodology. It's an increasing one. It's exactly the opposite. Then we have a look on the biochar. The biochar is a little bit decreasing, and here we have an increasing curve. That means a temporary sink that is generated year by year, can be measured properly, how much carbon was stored by the tree, by the forest that we have in the sea sink unit, and at the end it's a sellable carbon dioxide removal value on the market. Let me jump in a short dilemma. It's not only a small one, it's a big dilemma in our point of view. For the temporary carbon sinks, for the temporary carbon dioxide removal, isn't really a market out there. It isn't because we count in long-term periods, at least 100 or more years, and that's why Carbon Standard did develop a new methodology, global cooling. It's a methodology which includes all the temporary carbon sinks out there. Can be sold on an annual basis, and it's quite a new approach. And you can get more information on our website about it. Global cooling, probably the base of the new carbon sink economy. I think it's the final slide from my side. In our point of view, we have to think about more about planetary carbon recycling. To reuse carbon, as example, first we start in the snowboard, we will recycle it, we will use it somewhere else, and at the end, everything what we remove from the atmosphere, from the oceans, we can use somewhere. We should reuse it, like we have experts here in from the recycling industry. It will also be the case for carbon in our point of view in the next years. And it's our expectation that the most of all the sea sinks out there in future will be temporary. Temporary based on, because they are applicated somewhere in a product and will be recycled again, but stay then in the recycle process, also a carbon sink. Thanks for your attention. It was a short overview about our biochar standards and carbon dioxide removal standards.
Thanks, Ueli. Thanks a lot. And you even used a little less time than you had. So we now saw that the use cases, for example, they determine the permanence. So it really does have an influence, and it's key to know what you use it for. We also see that rigorous MRV systems are needed. So it's quite an effort to put all this technology and this thinking behind it to kind of track these carbon removals. And now we want to pass on to one of the really big questions, I would say, biochar's persistence or permanence in the environment. And who would you ask? Who would be more suitable than you as a professor in geochemistry, a domain who has been looking at organic carbon since, I don't know, a century? And lots of studies and lots of knowledge has been accumulated. So please, Hamed, go ahead and enlighten us. Yes, we'll try.
Okay, good afternoon. It's a great pleasure to be here. Thanks, Harald, for the introduction. It's a fancy title, but as a carbon geochemist, the real title that I like to present should be this: why I like biochar. And that's really come down to this. And I can tell you why. It has something to do with the carbon cycle. I teach carbon cycle in the Aarhus University, and when I look at the carbon cycle, I like biochar even more. Let me explain to you. If you Google carbon cycle, 90% you're going to see something like this: a fancy green cycle with a lot of greens and nice things. And then you see down there geology, fossil and fossil fuels. There's always a culprit there. And that's how we mess up with the carbon cycle, is basically burning fossil fuels and limestones and carbonates for cement and auto and our industrial activities. So this is basically how we mess up with the carbon cycle. And the first solution it comes to mind is if we basically open the earth and put the CO2 back in the ground. And that's really marvel of technology is happening now. CCS, you probably heard, and that uses the physical trapping of CO2 by putting CO2 into the deep strata of Earth. And in this case, CO2 is basically compacted. It's still a CO2, but we are betting on the hundreds of thousands of meters of rocks to keep the CO2 under the ground. And there is a great science and engineering behind this, and it works. It works by keeping a large amount, a scalable amount of CO2 stored under the ground. But is this how Earth store or remove the CO2? What does actually Earth do? Does it use the physical trapping? For that, I'm going to show you more realistic aspect of the carbon cycle. So we got actually two carbon cycles. One is in the top. That is the green, nice carbon cycle that I showed you in the previous slide. This is a carbon in the biosphere. Basically carbon in the ocean, atmosphere, permafrost, soil organic carbon, all the things that we know it exists in the biosphere. There is a nice quantity of carbon cycling in the biosphere, about 47,000 gigaton of carbon. The annual to millennial time scale is required for carbon to cycle in the biosphere. But down there we have another cycle, which is carbon cycling in the geosphere. So this is much larger carbon pool, about 80 million gigaton of carbon. And the cycling here is much longer, is a multi-million year time scale. These are like limestones, sedimentary rock, organic matter, coal, oil, and gas, all of these that we know. And that's how we mess up with the carbon cycle, by releasing this into the biosphere. So the question is, how does the carbon goes from this short scale biosphere to the geosphere? Is it a physical transferring? The answer is no. Is actually there is a layer in between. That's the surface of Earth, is a thin skin of the Earth, like a ocean surface, like soil, just anything on the surface. And the process is a transformation. It's called biogeochemical trapping. The carbon is chemically or molecularly or biologically is transformed into the geosphere, not by physical action of moving carbon in there. It's simply on the surface, by gradual process, carbon is gradually becoming more and more stable and is more preserved. And then eventually, the biosphere processes are no longer able to degrade or cycle or alter this carbon. So it's only the geospheric processes are capable of doing that. That is how carbon, a large quantity of carbon, through the geological time scale, is transferred from biosphere into the geosphere. But I'd like to open up this biogeochemical trapping or this transformation a little bit more. It's very simple. It's two simple processes. CO2 in biosphere could either use the process of mineralization. I know a lot of you heard about this, and becomes a carbon mineral. That's inorganic carbon trapping. The other method is organic carbon pathway. Not as a popular word, but believe me, that's a word. It's a maceralization. It's very much same as mineralization. It produces carbon macerals. What are these processes? In the process of mineralization is a chemical weathering. You heard of it, silicate weathering or carbonate weathering. Process of maceralization is organic carbon maturation, is how the organic carbon becomes carbonized. It becomes enriched in carbon, or the process of carbonization. The end product of these two for carbon minerals is carbonates, like limestones. And for carbon macerals, it's a new word, is inertinites. It is the type of organic carbon that is the most stable in the sedimentary rocks in the Earth's crust. So the main purpose of this process is to bring CO2 in a biosphere and convert it to the most thermodynamically stable form of carbon to stay forever, to stay in the geosphere. So this process is responsible for 64 million gigaton of carbon in the inorganic pathways, and for the inertinite is responsible for 15 million gigaton of carbon. So these are not small numbers. We are not sitting only with the carbon on the surface. We got significant amount of carbon and amazing processes taking place as we speak in the geosphere, and that's how the carbon is being stored. But how does it relate to biochar? So we are probably interested of this organic carbon pathway, as you may guess. And let me open up this one. Well, the biosphere conversion to inertinite is happening in two ways. One is, as I said, organic carbon maturation or a slow carbonization. So if this is a surface, so as the organic carbon is buried, it goes through various processes, which we call it diagenesis, catagenesis, and metagenesis. And that happens through the long process. And essentially, all the volatile carbons are being released, and the degraded organic matter is eventually converted to the inertinite, which is the most stable form of organic carbon. The question is, what does happen to the molecular composition of biomass? Is basically it becomes aromatized, it becomes condensed, the molecules become very fortified, it becomes very strong, and that's how inertinite look like. It's a very refractory molecule that is not breaking down in the biospheric process. Well, we do have a shortcut for this process where we could get the CO2 in a biosphere and convert it directly into the inertinites. Oh, it's not happening there? Oh, I need to do it there. Sorry, I thought it is electronic here. But, okay, I use this one. Anyway, this process of shortcut happens in nature by charring, in a wildfire. We see that natural wildfire or geological wildfires, they do produce something similar to what we call it biochar. And this material, if they reach high enough temperature and high enough molecular stability, they are found in all sorts of sedimentary rocks, not only coal, but virtually any rocks, shale, mudstones, mud rocks, any rocks that you could see that. And we see them hundreds of millions of years sitting there quite happily. So the other process is being done synthetic, so it's a pyrolysis. Pyrolysis would imitate the same things. And if it reaches enough temperature and it is done purely and correctly, the end result is the inertinite, and it basically works in the same way as the slow carbonization. So now we are following a rapid carbonization, but the end product is something that is the most thermodynamically stable form of carbon. And this is the question now. So if we are looking at the biochar as a carbon dioxide removal, and the main question is the carbon storage security or carbon permanence, we have a very nice established benchmark for that, and that is the inertinite, which that's how Earth does it. And the question really has to be, is the biochar equal to inertinite? Have we reached to the molecular structure and composition that is equal to inertinite? And for that, we tried recently to answer these questions, answer the benchmarks, by writing 80 pages paper, which is most of it is actually textbook material, but we also studied about 64 biochars from industry in order to look at the differences between the inertinite as a benchmark and the industry biochars. And I take a couple of slides to show you what we found. One thing is we know that as the pyrolysis temperature increases, the molecular aromatization and condensation increases. This is well known, it's nothing new. And by structuring and ordering of the organic molecules, the random reflectance, the reflectivity of the organic molecules increases. This is the parameter that can be measured very readily, and it has been going on since 90s. People know these things very well. So by measuring the random reflectance, we know that we are at the higher stage of the aromatization and condensation. And the benchmark is the random reflectance of 2%. We call it inertinite benchmark, or IBR 2%. So anything above this 2% line is inertinite. And this is not only me saying that. This is a science many decades old that we know based on numerous geological observations that anything above the 2% is per definition inertinite. And I don't have to translate inertinite to you. You know that they call it inertinite for the reason. And I guess this is the last slide. This is the summary of all the industry biochars that we looked at. And on the y-axis is a random reflectance, and in the x-axis is the amount of hydrogen. It's kind of similar to hydrogen to carbon ratio, but we call it hydrogen index. And the benchmark for inertinite is this area. And you could see overwhelming majority of the industry biochars are comfortably fall in the category that we could call them inertinite. They are in fact pure inertinite. You could use them as a geological standard to demonstrate inertinite. And that's really good, results as far as the biochar concerns. The rest also may not be pure inertinite, but they have substantial amount of inertinite within them. And that brings this notion that why I like biochar so much because, as I explained to you, it imitates the natural processes. By making biochar and using the pyrolysis method, we release energy and we leave behind carbon as a storage. And that's exactly what the actual carbon cycle do, converting the organic carbon from biosphere into the geosphere. That is how it works. And it's a generous way of using carbon. We use the energy and we leave behind something for the nature. And this is what I usually tell my students. We have started messing up with the carbon cycle long before fossil fuels. It was when we have started making fires. Because in the nature, we rarely have process that combust the entire carbon into the CO2. Usually the processes are mostly biological processes. Occasionally we have wildfires, but those are not really full of oxygen. They're oxygen depleted in most cases. So the processes usually generate energy, but leave substantial amount of carbon behind. But we've got really good at it, and we're now able to combust the entire carbon and pump it as a CO2 into the atmosphere. And that is why pyrolysis and pyrolysis energy and biochar becomes important, in my opinion, because it's a corrective step towards sustainable carbon handling. And this is really why I like biochar, and I can end it here. And I'd like to thank all the co-authors of that big paper that I mentioned, a lot of students and a lot of intelligent people that I have a pleasure of working with them. And of course, EBI, Geological Survey of Denmark, and Aarhus University. Thank you.
Thanks a lot, Hamed. So I have asked you so many questions already. This is why I would just leave the room. 2 questions to all 3 presenters. To you, please go ahead if you still are capable of asking questions. Lucia,
Thank you very much. Thank you to all the people in that panel. Very interesting, super interesting. I have a question for Professor SANEI. This is, of course, a super interesting angle to measure things. And I was wondering, do you think this is enough for the industry and for the liability of selling credits from biochar for removals? Is that enough, or do we need something? What do you need more, if not?
I think the question of permanence in biochar is a big distraction for other important things, such as the yield, toxicity, all other things that is related to the application of biochar in soil. I think if biochar is qualified as inertinite, which most do, and it's very easy to do that, it's very easy to measure and certify, I think that's it. We should move on and try to look at applications of biochar and all other things that you mentioned. So this by itself for permanence is enough to me, but by no means is enough for other applications of the biochar in terms of toxicity, yield, all other things. But for permanence, I think we should really move on as quickly as possible, because I'm not talking controversial science. I'm talking science, geochemistry, about century old, and these are well understood things. We can recognize and quantify and understand inertinite in the same way that we can tell mineral of carbon. It's not a mystery. We know what is inertinite and we know what is carbon minerals. Well, if it is, then we should move on.
Please. Yeah. Sorry to hijack the question from the room. I have a provocative follow-up questions on this to Professor SANEI. So you explained that we find in nature, we find inertinite in sedimentary rocks, shales, and all these formations. Does it mean that we have to bury biochar to achieve the same impact?
No, because virtually all the biomass were on the surface at some point. So a lot of inertinites that we see in the rocks of 100 millions of years, they were on the surface. They were buried gradually. Some of them, they've been cycling in the biosphere on the surface for thousands of, tens of thousands of years. See, this is my question. I turn it around. If we say that inertinite, which is basically most biochars are, if we say inertinite degrade in biosphere, we have to be prepared to accept that no organic carbon would ever make it to the geological rocks. It would not be possible because that's the most thermodynamically stable form of carbon. And if you tell me that the processes on the surface of Earth are so potent, are so aggressive that they would virtually combust everything to CO2, then why should we have any organic carbon in the Earth's crust, where we have 15 million gigatons of that? So it's just really a question about the carbon cycle. So burial would, if you bury it in a, let's say, 2,000, 3,000 meters, of course, there won't be much bacterial activities going on. It would help, but you really have to go below 2,000 meters to make a big difference. Because we know up to 2 kilometers, 3 kilometers, bacteria could happily function.
I'm looking at the audience in order not to hijack the next question that we have to.
Hi, sorry, follow-up question. So if the permanence of the biochar is forever, why the current verification methods will only classify biochar as 100 years plus, not 1,000 years permanent storage like some of the other CDR options? Tough question, sorry.
My answer is I don't know, but I'll let Harald say.
Yeah, it's kind of a difficult one to answer, but I think the person closest to it is sitting on the other end.
Yeah, thanks for the question, James. Of course, the scientist is sitting over there. I think always if we develop new systems, new industries, new business here on the planet, we always have to be a little bit careful how we implement that. All of us, we know that application of biochar on the soil level or as animal feed product can create huge additional value. At the end, we have the possibility to increase soil organic carbon by application of biochar, as example in compost. And for us, it's wonderful, and thanks to Professor SANEI for all this work that you are doing until now. And I think this is the short answer, the short part. The scientific evidence of the different biochars out there with soil application was not so clear that we could say, okay, in each case is 95%. That's why we are also a little bit on the safe side of everything. And if these scientific proofs will get real, also from the science out there, from the different scientists, then we still can also increase the part and value of carbon sinks in our registries.
And just to add on to this, thanks. Of course, you have to be conservative, and I know the 100 years question that was there because people were asking what is the most relevant time scale to mitigate climate change. Now we have a tool to finally look into biochars and not just use it at this material, like it's this black stuff that has somehow been carbonized, because there are also different processes to carbonization. There's also torrefaction, and I bet you would have a difficulty differentiating if you look at a torrefied piece of wood or a carbonized, like pyrolyzed piece of it. It might look quite difficult. It might be quite difficult to differentiate those two. So two things. One, we can now look into the different fractions of biochar, and Hamed has classified them into 4, but you could even define them in more, maybe 15 or so, I think you said. And the other thing is, what is biochar? So now we have, or Hamed has, I have done nothing. We sent some samples, but we've sent some representative industry biochars. Like, what is the state of the art? What are we just producing? Not what is possible to be produced, but what is like a random sampling of biochars that are currently produced within the industry by you, by those people just in the back. And this is a difference from what has been analyzed before. Is a tremendous difference, actually. So before, if you look at anything that has somehow turned black because someone exposed it to heat, makes a difference if you do that, or if you look at actual biochars that are being produced and used currently in industrial processes, and not forest fires, and not torrefaction, and not someone who dug a hole in his backyard and produced something and then sent it in. It's exaggerating, right? But this variety now needs to be defined, clearly analyzed, and this is possible. And I think there was a question.
Can I just add it quickly? Because I think this question is important, and indeed the problem is very much related to a mistake that we keep doing. And this mistake is that we talk about CDR methods as one thing. So biochar, one thing. BECS, one thing. DAX, one thing. Totally wrong. And we need to now start differentiate between the different kinds of biochar that you can produce. And also maybe it's okay to produce a low permanence biochar for certain uses, you know. If you are to compensate biogenic emissions, for example, totally okay. So I guess the future is in a future where people can produce whatever biochar they want, but then they have to prove the share of the high permanence fraction, and that's fraction they can sell it as a high permanence, and the rest they sell it low permanence. So I think that's very important in all the conversation we have also with policymakers, that they understand that there is a huge diversity within the CDR methods. Same applies for DAX, for example. You discuss direct air capture and people think of the first generation concepts like carbon engineering, super energy intensive, burning methane to run the process and all this. And now we are already to the third or fourth generation where there's nothing, I mean, it's like passive, you don't need any heat, so you have very different concepts. So it's very important to break things down so that we know what we're talking about.
Hi there, Adam Samuel from Capture. Thank you guys for the talk so far. My question to you is, do you think as an industry we have a responsibility to do more real-world demonstrators? You talked about if permanency, we can get over this hurdle. We might look at things like toxicity. Do you think we do enough demonstrators? Because we have a lot of academic evidence at lab scale, but not necessarily at field scale. In the UK, we have maybe 200 tons of biochar being spread on land. We're miles behind.
I can start if you're happy. I think that's a very good question, and my answer would be yes, more demonstration, please, for different reasons. I think demonstrators are very helpful on a technical perspective first, to acquire data, optimize process and all this, but we all know that there's also a massive, like, looming issue of public acceptance of all these techniques. People have become, for some reason, very reluctant to any kind of climate solutions, actually. That's becoming very tricky. And so, and people are struggling to understand what we're talking about when we talk of CDR. Well, biochar probably is the easiest one to get, right? But I think just for that, it's really important to have demonstration that people can visit, journalists can visit, and people can realize that it's okay, it's just a container, you know, emissions are not toxic or whatever, but they need to see it, to touch it, to smell it. I think it's super important. So, and I think this issue is looming, I guess, I said, because everybody knows it's there. We haven't found the right solution to address it, so we are pushing back, but that will come back, you know, this year, next year, but not further than this. I don't know if anyone wants to.
Yeah, exactly. I have the same opinion. I think we are ready for all these explanations. And if you look at out there on the market at the moment, then I'm hesitating a little bit to think that we will be able to scale the market as we expect it, and how we should scale it from the climate perspective. As example, if we think only about soil application, I know how farmers think. It's not so easy to convince them to use a product. But there are so many possibilities out there. As example, in Switzerland, a guy is building a house now based on biochar concrete, with biochar everywhere and hemp straw in the bricks. And at the end, this building will be climate positive. This is the point, can even be certified as a carbon sink. And that's what we can demonstrate with our products, and let's do it now, because we have to scale up this market and not to think about the problems that we have in the background.
Wonderful. If you want to see some real life implementation of biochar-based products, I've seen just walking around here someone who put it in concrete. I don't know if it's Castorcon or Ecoloct. I think it was at their booth. And Bart, my friend over there, is just 3D printing with biochar-based polymers. So there are different time spans of permanence, I would say, of use of these materials, but they are existent. And we as EBI, we are in discussion with the EU Commission on potential delegated acts after the CRCF. And then, of course, in their interest, it is also to have something graspable, something tangible. So urban environments would be a lot more interesting, actually, than rural environments where nobody can actually see what's going on. So furniture, concrete furniture, we've been discussing this. You can 3D print maybe even the furniture in cities, and then you have urban trees planted in biochar-based substrates and all of this. This makes it graspable for people, and this should be the approaches. So absolutely right. I think we need to stop putting this debate about permanence aside, as it's becoming clear now where this is going, and refocus on the use cases and on scaling of these applications of biochar, because we can do so much good. And that's it from. Do we have more time?
It's going to be the last question.
Krista, maybe? Or do you have someone? So these are going to be the last questions.
Okay, thank you very much, and thank you for the presentation. I have a question probably to Professor SANEI and Mr. STEINER. Professor, could you expand a little bit on the quality and efficiency of different biochars, particularly the biomass that they were based on? I am particularly interested whether you had some sort of biochar based also on sanitary waste, so really going back to basics of biochar. And the follow-up question to Mr. STEINER, to what extent certification is following also or exploring that type of biochar to be certified? Thank you.
Yeah, if I understood your question, in terms of biochar, once it becomes inertinite, the type of biomass is immaterial. It's not relevant anymore. Basically, the inertinite biochar, there's nothing biological about it anymore. It becomes a polymer. It becomes very highly refractory polymer, and it's really not important what type of biomass you have. It does make a huge difference in what is being generated to get to the biochar. Of course, the amount of, you could produce biofuel, different syngas. Of course, those are very important, and ultimately the yield. But in terms of the biochars, as soon as it reaches the classification of, to me, is inertinite, is inertinite. And of course, there are a lot of good other EBC and other standards that are mentioned with regards to toxicity. Those should be very important also. But in terms of permanence, that's what I have to say.
Yeah, thanks for the question. I would like to answer it in two parts. The first part is the question of the biochar himself. What we have to know is that the feedstock, production procedure, and everything on the way of having the biochar in the bag is influencing the quality of this product. And this has to be measured properly at the end, and that we know what is in this bag or in this truck to know what kind of biochar we have. And the second part of the answer is on the level of certification of carbon dioxide removals. At the end, it's a three-step procedure. First, we have to know what kind of biochar we produced. Then we have to check, as example, the efficiency of the carbon inside. Biochar C-Sync, the new standard from us, will contain the efficiency label, as I showed quickly before. And then the third step, and that's the most important one, is where this biochar is applied, the matrix. And if you apply to the concrete, then you have 100% inertinite biochar, because the biochar is still in this concrete until the house is no longer there, as example. But if you apply to the soil, that means it's a different story. And the windmill blade propeller is again a different thing. That's why the application in the matrix is then the third step that is really important in the certification process.
Yep. So I think we've reached the end, and we have no more possibilities for questions here, but we do have them later. So we have a EBI booth, and the presenters will also be around. So just catch them, ask your questions, maybe group together, because there might be some other people having the same ones. We're happy to see you at our booths and later around. Thanks all for your interest, and yeah. Let's talk later. Thanks to the presenters particularly, because it was wonderful.